Students, welcome to lecture number 14. As I discussed in the last lecture, we are almost 1/3 through. So soon we will start discussing about the statistical and the computational methods using machine learning. But let me take you through the remaining part of the processing of materials. So as you know, we have been discussing about different processes by which materials can be made. Not only materials, even components can also be made, right? So that's important. You must be thinking why we are talking about these aspects, because machine learning is not only for discovery of new materials, but it is also for innovating new processes, or even understand different steps of the processes which can be further modified or even innovated. That is why we need to know what are the factors which control the different processing of or the processing methods of materials. So we have discussed about these particular slides probably many times, and it must have been gone into your brain, imprinted, right? The material tetrahedron, and that is the key thing of any materials processing, design, structure, because the connection of structure property correlation along with processing is what is needed to be known if you want to design new materials, if you want to design new concepts, right. So therefore we have started discussing structures, then we deliberated on different kinds of properties. I can't discuss everything here because of time constraint. Finally we talked about processing. We are now discussing about that. So processing operations, as I discussed again and again, I am telling you, because this is something which you must know very well. There are three categories of processing operations. First is the shaping operation, using altering the geometry of the starting workpiece of material. That is for casting, deformation processing, powder metallurgy, that is what is done. Second is the property enhancing operations, which is routinely used in material science, that is heat treatment. We can improve the material physical or even sometime many functional properties without changing the dimensions or changing the shape of the material, right. Many cases, in fact in today's world we only talk about the electronic material using 2D materials, electronics using 2D materials. This is very important because we are going to generate different 2D structure, and after that we do a lot of post processing operations where we do not change the geometry or shape, but we change the material properties. That is what is called property enhancement operations. And in material science or metallurgy, it is basically mostly heat treatment, correct. In a heat treatment is a very age old word, but it is used by everybody, whether it is material science, metallurgy, physicists, even chemists. Third one is what is known as a surface processing operation. It can be used to clean, treat, coat or deposit material on the exterior surface of the object or the workpiece. So I am not going to discuss about these aspects, because this is a very open field, like whether you want to coat something, deposit some materials or do something that encompasses everything we see in the world, starting with the walls of the room to the floor, or even coating the materials for solar panels, everything. So therefore it is not possible to discuss even these kind of aspects in these kind of lectures. Rather we should know that there also exists a lot of processing parameters which can be used as a features or factors to do machine learning operation, and for that you need to go into deep into that process, understand the process. That is what is my purpose is. I am just telling you the tip of the iceberg, you can say. Why? Because if you want to do machine learning is a very fancy word, right. Everybody wants to do machine learning today, everybody wants to do AI. Even many students, those who are want to do undergraduate studies in different institutes in India, for the first choice is AI. God knows what has happened to the generation, but AI is something which is broad, and ML is only a part of the AI. So if you want to do machine learning of anything, you should know the conditions, the processes, the aspects of the making the things very well, then only you can do machine learning. Remember this aspect very well, because many times we ignore that. We started behaving like a semi-computer and started modeling it without knowing anything about it. That is not the right way to do it, and that is why we are discussing about these kind of things, material structure, the properties as well as processing conditions or processing things. So, we talked about solid lubricant processing already, right. We discussed about processing, how to shape a material from the liquid or semi-liquid conditions. Then we were discussing about the deformation processing first, and then slowly we will go to particulate processing and a bit of machining, because machining is a subject altogether, it is not a small thing to do. So, therefore, this is the whole thing actually. What are the things? Shaping operations, casting, powder metallurgy, ball deformation processes and machining, and this slides is again repetition. So, as far as the property enhancement operations, the major thing is heat treatment, and for heat treatment you use a TTD diagram. I explained to you, TTD stands for transformation, temperature, time and transformation. There are 3 T actually. One is T, temperature, other one is time, and third one is a transformation. And these diagrams are generated to understand what will happen if I cool a particular workpiece in a particular rate. That is what is shown here, the 4 possible pathways, right. You can see the lines, the curves which are coming down, there are 4 possible pathways. And superimposed on these is the diagram which talk about different phase field like austenite, pearlite, vanite, martensite for steels. So, you can generate this kind of diagrams for any steel composition, and in fact these are all available as atlas. You do not have to generate it. You should know how to read them and how to know that which are the parameters controlling the microstructure, and that is how controlling the properties of the steels. So, as you know, we start with austenite always. That is a FCC phase which can accommodate a lot of carbon in steels. Almost 2% carbon can be accommodated at 1150 degrees Celsius temperature. Now, rest of the thing is how do you partition the carbon, whether you partition by diffusion control process forming alpha iron and cementite, or you do not allow a diffusion to happen, so that you form martensite, or you are in between, you are like a isothermal heat treatment in the intermediate temperature, let us say about 350 to 450 degrees Celsius temperature for iron carbon phase diagrams. That is how actually these kind of things can be controlled, and this can lead to different kinds of phases and microstructure, and each microstructure has different kinds of properties. So, pearlite is the classical example, everybody knows, very clear, even in the books of standard books it is very widely taught. So, austenite to pearlite transformation is the simplest one to understand. The diffusion control transformation, diffusion of carbon is the main factor, and it leads to lamellar microstructure, and by controlling the lamellar thickness you can control the mechanical properties, very clear. Martensite is different, it is a body centered tetragon structure, and it is basically much harder than pearlite. So, in a very fine scale, this is how the pearlite will look like, alternative plates or lamella. You can see that, right, that you can see the white and black, white and black, white and black, like that. Remember, this is an in situ composite. We talk about composites like last time. There is an in situ composite between 2 phases. One is a soft phase which is alpha iron, other is a hard phase which is carbide Fe3C, and this provides the steel the wonderful properties which no material can replace in the world so far. So, if I want to do machine learning modeling, or if I want to do machine learning modeling, my first choice will be to use steels, because steels have a lot of variation and it is a widely studied subject. Machine learning can be done because data are available, lot of experiments and computational things has been done, and by simply changing the heat treatment you can create different kinds of mechanical properties. This is to show you that how this kind of mechanical properties can be obtained. Okay, this is just an example. Then we talked about surface hardening or case hardening, right. We took the example of gears, and gears are very important for drive. You want to transfer the drive in cars or trains or any other kind of objects, machines actually, gears are important, and every gear has multiple teeth, and these teeth actually undergo a lot of wear and tear. It can even crack, it can even break, it can even undergo all kinds of failures. In order to stop that failure, what you should do? You should do this kind of surface treatment operation, carburizing, nitriding or carbon nitriding, and carburizing is nothing but adding carbon to the surface of the gear, and this can be done simply by exposing this part of the gear, top part of the gear, these are the teeth, in a carbon rich atmosphere at an elevated temperature, so the diffusion can happen faster, and diffusion can lead to a lot of carbon going inside these thin layers, and that is how it can form a very hard layer of carbide. And carburizing can be many different types of processes: gas carburizing, plasma carburizing, salt bath carburizing, pack carburizing. Each process has different parameters. That is the purpose of showing you this. If you are going to use machine learning for industry which is utilizing gas carburizing, you have to understand what is gas carburizing, what are the things, parameters which control the gas carburizing. This will be used as your features, and then develop an ML model on that. Well, you can clearly see from this picture I shown you last lecture also, the thin layer of carbon region on the top surface of this teeth, and it's very clearly suggests you or show you that carbon indeed diffuses inside through these surface layers and form a thin layer. Now, nitriding is much more complex things, not like carburizing, and it is not easily can be done. Obviously, best way of doing nitriding was dip these gears into a nitrogen containing salt, and earlier days people used to use cyanide salt, sodium cyanide, potassium cyanide salts, right? But now environmental regulations do not allow us to use this kind of processes. So that's why you can use plasma nitriding. You can have a plasma generated inside a chamber, nitrogen plasma, and that nitrogen plasma will have activated nitrogen ions which can enter, which can be implanted rather, inside these surfaces of these gears. That's how it can be easily done. Or we can actually do induction heating also. Induction heating will lead to surface to be heated up and then quench. That will lead to martensitic formation. So then we talked about a little bit about precipitation hardening, which is used in aluminum alloys, aluminum copper basically, but there are many alloys: aluminum, copper, lithium, aluminum, other alloys also undergo this kind of transformation or phase transformations or hardening. And this is what is done here. Basically simply it's also heat treatment process. You don't do much. Remember, many of the aluminum alloys, after making the component by some routes, either casting or deformation, they are given this kind of heat treatments, where it is heated first to the single phase field like solutionizing temperature Ts, single phase field kappa, then this is quenched. So the supersaturated solution is retained at room temperature, and then if you heat it up little bit high temperatures, little bit higher, not more than that. For aluminum copper alloys, 150 degrees to 170 degrees will be enough. 170 degrees Celsius actually I am talking about it. And if you keep it for extended time, these precipitates will form, that will lead to hardening of the materials. And this is how the microstructure will evolve. Actually here the microstructure play a very important role. You have to understand this microstructure which are basically generated by formation of these precipitates, they have a role. The number of precipitates, size of the precipitates, distance between the two precipitates, they all actually play a role in making the things material harden. And one can have different kinds of precipitates. This is showing how the precipitation hardening happens. The starting microstructure is a kappa and coarse precipitate. If you heat it above the Ts temperature, solution temperature, it will form a single phase supersaturated solutions and quench it. If you heat it up, it will not be supersaturated solution, it will be solid solution only. But if you quench it to room temperature, this will be supersaturated solution, and then at room temperature nothing much will happen. That is why you have to heat it up at some elevated temperature, intermediate elevated temperature, and to form these fine scale precipitates. And these are some of the pictures I shown in the last lecture. Well, I just wanted to discuss more on this metal forming operations, and that is what is the purpose of today's lecture. So there are a large group of this manufacturing process in which plastic deformation of alloys or metals are used to change the shape of the workpiece, and basically tool is nothing but a die, and you can apply stresses either tensile or compressive or shear. We discussed about this aspect much earlier, and the metal can be, shape can be changed. You can heat it up or you can do it at room temperature also. So basically there are different operations, the direct compression type operations, indirect compression type operations, tensile type operation, bending processes, shearing processes. Okay, you can clearly see this is bending, and this is bending operation is application of bending stress, and then this is a shearing operation. Okay, deep drawing is also a compression, correct, extrusion is a compression. Only tensile force applied is here, stretch forming. You can actually take a sheet and stretch it apart, and that can lead to decrease of thickness of a sheet, and that is the only tension type process. Remember, tension type process can lead to application of tensile force can lead to necking and failure. That is why the tensile type processes are not widely used. Most of the processes actually are used as compressive type forces. And we discussed about rolling, forging, and I talked about all the processing parameters, some of these things, and extrusion, and as well as wire drawing and sheet metal forming, right. This is all we discussed about in the last lecture. This is sheet metal polishing. One is simply bending, and then you have a deep drawing operations. This is also you have seen how a sheet can be deformed extensively and to form a cup, the cup which you use in the home, metallic cups for drinking coffee, tea or something produced by the same root. And then we can cut it by using shearing operations also. So now let us talk about how these stresses actually are affecting the material behavior, because this is something which will be used as a parameter or feature in your level model. So what are the things required? Desirable material property requirement for this kind of operation is a low yield strength, because here you are deforming the material in plastic regime. So therefore you like to apply less stress so that your machine does not get affected much. That is why in many cases we increase the temperature, because by increasing temperature we can have low yield stress, and also obviously we need high ductility. Material should be able to deform. In fact, you remember I have shown you also that if I increase temperature, the yield stress drops and ductility increases. So that is why majority of these metal forming operations are done at high temperatures. And other factors also important, like strain rate and the friction between the die and the workpiece, because friction can generate also heat, friction generates also stress. So therefore this is also important. Strain rate is what? Strain rate is the rate at which you are deforming the material. So what are the principal parameters? Okay, this equation I shown you, right. So you can see that this equation, something is at the background which you can see. So this is the fundamental equation depicting the material behavior during metal forming. The true stress sigma T is equal to K epsilon to the power n, where K is the strength coefficient and n is the strain hardening rate, the exponent. Now stress and strain actually dependent on each other by this equation. This is called a flow curve equation, remember, and this dictates the material behavior when you apply stress. This is engineering stress strain curve. Can you see that very easily? That is first elastic, then the plastic portion. We will not at all discuss the elastic portion here, because we are going to work in the plastic design. We are going to work in the plastic regime. That is why we are interested here in this part of the flow curve, and thus equation is this. So what are the material parameters which are important? K and N. These two parameters you should have values for different materials. So if you look at different books, these values of K, N will be given. That dictates the value of sigma T. So if you want to model it, you do not need to model using sigma T or epsilon. You need to model using these parameters. So other than that, there are many other issues like ultimate tensile stress, fracture stress, strain to fracture, strain to failure, uniform strain, lot of things are important. Well, flow stress is what? This is the instantaneous value of the stress required to continue deforming the material. That is what is flow stress, and this is easily obtainable by this way. This is nothing but simply I change the rotation from sigma T, it becomes YF, but otherwise it is same. So you can also write down sigma T. So now there are other parameters which can be used. Important parameter which can be used is the average flow stress, that is equal to area under this curve, right. You can clearly see that this is K epsilon to the power n divided by 1 plus n. Factually speaking, it should have been K epsilon, it is integration, so that is why actually. So now by integrating the flow curve equation between 0 and the final strain value, a region of interest, one can do that. This provides you average stress required to deform material. This is a very important parameter which can be used for machine learning. As you know, K and A both depend on temperature. So therefore, both strain and strain hardening rates, strain hardening are reduced at high temperatures. I have shown you a table also, you can go back to my lectures on mechanical behavior, and that is why ductility improves at high temperature. So K and N can be directly used instead of other parameters. So that's why based on temperatures we can have different metal forming operations, whether it can be cold forming, cold working, warm working and hot working. How do you differentiate that? How do you define each of these processes? Let us see that. This chart is very important, this picture. I know what happens when I start deforming material as a function of temperature. So if you start deforming material, you will generate a lot of defects. We talk about some defects like dislocation, twins, stacking faults. So these defects will be generated all throughout the material. That is what is shown here, you can see here, a lot of dislocations are generated. Now if you heat it up high temperature after deformation, these dislocations will arrange themselves nicely. That is what happens in the materials. Once they arrange themselves nicely, it can reduce its energy. Remember, if I generate a lot of dislocation simply by hammering a piece of a metal, I will generate a lot of dislocations, right, because metal is getting hammered, it has to plastically deform. Only way of plastically deforming this by generating a lot of defects, and they will be generated randomly. So therefore, they will not be having time to align properly so that they can reduce the energy. So once you heat it up, first thing will happen is that they can align properly, reduce the energy, and in the process what will happen? In the process the grains will recover slightly from cold working. That is what is called recovery. You can see here, that is what is called recovery. This is exactly what happens. So if you measure electrical conductivity will increase compared to the cold work material which is deformed already. Now if you heat further, new strain free grains will form instead of the grains which have lot of defects. New strain free grains will form, that is called recrystallization. Okay, you can see there, that is called recrystallization. That normally happens almost half of the melting temperature of the material. Whether it is alloy or pure metal does not matter, almost at the half of the melting temperature material. Now we can also, if you still heating up, it will lead to grain growth formation. These new grains will grow and they will become bigger. So as you can see, this is the microstructure evolution what is going to happen. Now if I see the ductility will be low when it is cold work and recovered, but as this temperature increases, ductility is increasing further because the stress is getting relieved by formation of the new grains or growing of the big grains. On the other hand, strength behaves opposite way. Strength will be very high in a cold work material or recovered material. It will slowly go down and reach a minimum value when grains have grown large, big size. So strength and hardness, they behave similarly, and basically hardness, it can be used to measure yield strength in many cases. Now what about the internal stresses? Internal residual stresses which will be there because of these defects will be slowly reduced as you increase the temperature. That is also evident because as you increase temperature, you are relieving the stresses, so stress will decrease. Therefore, using this concept, I can now say hot working is deformation at temperature above the recrystallization temperature. That is the rule of thumb. Now recrystallization temperature is about half melting point of the material in absolute scale, remember this. So let me give an example. Let us say for lead Pb, what is the melting temperature of lead? That is about 327, that is the melting temperature of lead. So now this is equal to 273 Kelvin, that we must know, that is equal to 273 Kelvin. So that means 600 Kelvin. So that means Tm by 2 is how much? That is equal to 600 by 2 Kelvin, that is equal to 300 Kelvin, that is equal to 300 minus 273 degrees Celsius, that is equal to 27 degrees Celsius. So for lead, hot working temperature is room temperature. Remember how I measured, I have to add 273 and then take the half of that. That is why it is in the absolute scale. In practice, hot work usually performs somewhat above this temperature, 0.5 Tm, and metal will continue to soften as the temperature increases above this, and that enhances a lot of advantages of the hot working. Many things, increase the ductility, reduces the yield strength, so therefore machine capability is required less. Many other parameters can be used, but only catch is that you have to heat it at high temperature, so you have to provide a lot of energy. Now hot working actually is very widely used and more widely used than the cold working or warm working, which will show you what are the warm working and cold working. And because at high temperature strain hardening coefficient becomes very low, almost close to 0, and ductility is very high, strain coefficient is substantially less at high temperature. So therefore this is practically a workhorse in the metal forming industries. And what about warm working? Warm working actually, sorry, not warm, cold working. Cold working, this is performed at temperature slightly above or slightly actually above room temperature, but it is between room temperature and 0.3 Tm. Many cold forming processes are important for mass production, like many steels are actually cold work. And the advantage is that you don't need to heat it up, energy consumption is less, and second, there is no machining required because surface finish is very good, and that's why these operations are near net shape operations, which is practically very good for coils or the different kinds of plates, sheets, everything used in automobile nesting. And warm working is basically nothing but temperature between 0.3 to 0.5 Tm. That's what it is. Sometimes it is useful because here energy consumption is less, metals will not oxidize also much at lower temperatures, but again it requires machining. So now that is temperature. What about strain rate? If you can apply high strain rate, you can deform faster. If I apply low strain rate, you deform slower. So strain rate is very important. But if I apply a lot of high stress, material may fail, break down. So therefore, we should understand what is the effect of strain rate on the material behavior. And fundamental equation is this for the strain rate measurement is nothing but velocity by h. You can clearly see this strain rate unit is second inverse. Unit of strain rate is second inverse, right? That is second inverse. So V is meter per second, h is meter, so then it becomes second inverse. That's why. So velocity of the ram or velocity of the movement of the equipment basically, and h is the distance or the thickness many times. Instantaneous height of the workpiece, it is written here. It can be thickness also. That's how the strain rate is defined. Here you can see that h is this, v is this. So you can easily measure what is the strain rate. So now to give you values of strain rate, tensile test uses strain rate of this much, 10 to the minus 7 to minus 3, hydraulic 10 to the minus 3, and explosive forming can use high strain rate. So we will talk about much of the strain rate in the next part of the lecture, where we will discuss how the strain rate is going to affect many operations.